And okay, so ignore the module 4 in the new textbook or with the new syllabus. This is part of module 3. So they basically combined from the previous syllabus, just combined these two modules into one. Not that it really matters because they actually already handled it as one module in the exams. Right, so yeah, so this is basically on X-rays and radioactivity. Again, there's a similar drawing in the book on an X-ray, what is it, an X-ray filament tube. So yeah, so there's a similar drawing. This drawing is just a little bit more detailed, but it has the same labeling and everything as the textbook. You guys are welcome to use this drawing if you want to. Have a bit more of a complex drawing, but I'll show you guys in the textbook as well. There is another one. But in any case, I'm not going to go through all the theory through electromagnetic radiation. What you guys do have to know, though, is what this. Yeah, so you guys have to actually know about the electromagnetic spectrum and how the waveforms or the electromagnetic waves are arranged with relation to one another. And I also just want to make the point here is that do not confuse electromagnetic radiation with ultrasonics. They are not the same thing, even though their behavior is very similar. Electromagnetic radiation doesn't need a medium to propagate, right? So it can actually travel through vacuum. So just keep that in mind. The best way, I don't know, for me, how electromagnetic radiation makes sense for most part is that it's actually light, visible and invisible light. Right. Okay, but just so you guys know, so in order of decreasing frequency, so meaning highest frequency to lowest frequency, you have gamma rays, X-rays, ultraviolet radiation, visible light. Then we have infrared radiation, microwave radiation, and radio waves as well. Right, so you guys can also get a bit of an idea how big the wavelengths are as well. So obviously, the higher the frequency, the shorter the wavelength, or the lower the frequency, the longer the wavelength. So you guys can see radio waves are in the order of kilometers long, while gamma rays are here in the order of picometers, I believe. So yeah, so very small and highly penetrating as well. All right, okay. So I'm not gonna, like I said, I'm gonna skip a little bit over the theory here. So there's also the three ways that energy can be transmitted. So you have your electromagnetic radiation, conduction, and convection. Now, conduction and convection kind of is dependent on energy transfer via media, whereby electromagnetic radiation is not dependent on that. And yeah, so okay, yeah, also very important for electromagnetic waves is that they travel at the speed of light. That's why I explained earlier that for myself at least, it makes sense that electromagnetic radiation is light. In fact, most of the spectrum is emitted by the sun in any case. so yeah. But yeah, in any case, that's the speed at which they travel. And you can actually go and calculate frequency and wavelength using this formula here, because we already know what the free space constant or the speed at which the waves travel. So if you know what the frequency is, you can go calculate the wavelength. If you know what the wavelength is, you can go calculate the frequency. And then we also distinguish between hard and soft X-rays, whereby soft X-rays have a wavelength close to the ultraviolet spectrum, and X-rays with shorter wavelengths closer, actually overlapping your gamma ray range. Those X-rays are known as hard X-rays. And yeah, so X-rays are produced by the transition of electrons. Now, it is a little bit different. Yeah, so light and X-rays is a little bit different in this sense. So light is produced by transition of your outer electrons. So you have the outer electrons um, moving towards your inner orbitals, and that then has a specific wavelength of light that it will emit. X-rays, very similar, in a similar way, will be generated in a very similar way, but you have the transition of inner electrons. So inner electrons moving from innermost orbitals to outer orbitals, and will then emit X-ray photons at specific energy levels based on the number of orbitals transitioned. All right, so yeah, so there's quite a bit of an explanation on how this happens. I'm not going to spend too much time here because there is actually some examples I want to go through, like the calculating the efficiency of X-rays. So you guys can go read through this. So as you guys can see here, for instance, yeah, actually it's the outer electrons moving to the inner orbital. So essentially what you have here is a electron basically colliding with an electron in your target, what we call the target material, and that then basically leaves a vacancy in the orbital, and then that orbital is then filled by an electron in one of the outer orbitals. Now, in this case, this electron jumped 2 orbitals, so you're going to have an X-ray photon. So actually there it goes, an X-ray photon generated with a specific energy level associated with it. So depending on what electron fills that orbital, that's going to generate an X-ray with a specific energy, right? So that depends on from which orbital. So for instance, if it's 2 orbitals, that's going to be a higher energy than some electron jumping over only 1 orbital. Right, so this is actually what's meant with the energy levels being quantified. So so basically if an electron jumps a certain amount of orbitals to fill that void, that's then going to generate an X-ray with a specific energy associated with that transition. All right. So again, X-rays will affect photographic emulsion the same way that visible light does. You guys should know this. I'm pretty sure all of you have been exposed to some form of X-ray photography, if I can put it that way, or radiography. So either a broken leg or some X-ray that you had to go for, medical X-ray. So yeah, that's actually what it's referring to here. So yeah, so that's how your bones can actually light up on an X-ray, because they have much higher density than your surrounding flesh, so they can actually absorb a lot of that X-ray radiation, or even reflect it. But actually metals reflect it quite nicely, so then it makes it like a bright flash on the emulsion, and you can't really see what's going on there. But anyways, then you have your power supplies. Now my diagram is a wee bit different from the textbook, but it is still the same diagram. The layout in the textbook is just a little bit different. So yeah, so you have an auto transformer that you can adjust. So it's basically, this is the power supply to your anode that we have here. So basically the voltage applied to your anode is going to be directly proportional to the amount of X-rays you can produce, or the energy of X-rays you can produce. So the higher the voltage, the higher the energy of the X-rays. Then you also have your cathode. Your cathode is then going to be generating your electrons to strike your target material. And yeah, usually this is run at in a saturated state, so that any fluctuations in your supply voltage will not affect your electron emission. Right, so kind of quickly, very shortly explain what happened here. And the thing is, the adjustable transformer is also to adjust for fluctuation in mains supply, that you have a little bit more control over your X-ray exposure as well, because it is highly, so because your X-ray emission is very much linked to your supply voltage. So if you have any variation on your supply and that then gets carried over, it's also going to cause variation in your exposure. Right, so that's something that we would like to avoid. Okay, so there are quite a few uses for X-rays. So the main uses is basically in scientific research, engineering, medicine being like pretty much everyone gets exposed to this form of practical application for X-rays. But in engineering, there's actually quite a few. So non-destructive testing and inspection. So what we did with the ultrasonics to do thickness gauging and to detect flaws in materials, you can do the same with X-rays. And I believe the textbook does, I think they do go into the testing methods here as well. I just want to make 100% sure if they do. Yeah, so you guys also need to know it. Yes, they made this module a bit dense. Sure, okay, this is alpha particles, beta particles, gamma particles. Okay, so this is actually quite new. So there's actually quite a bit in the book that I don't have in the slides. So I don't have the alpha, beta, and gamma particles in there. But anyways, yeah, I think I'll put up module 5's slides as well. Then you guys can go look at the testing, the testing methods for X-rays and ultrasonics there as well. So I'll put that up as well. Right, so calculating the efficiency of an X-ray tube. So we're pretty much going to have this formula here. And then we can also go and calculate the shortest wavelength of X-rays generated. So E is your applied voltage, Q is your electron charge, so that's going to be a constant value. Velocity of light in a vacuum, that's going to be a constant value. You can actually use the 3 times 10 to the power of 8 here as well, if you're not given this value. Planck's constant, also, again, that's a constant. So the only variable here is the applied voltage. So as you guys can see, if you have a fluctuation in your supply voltage, you're going to have a fluctuation in your X-ray energy as well. All right, and then radioactivity is, this is pretty much just theory. So you guys can go read through that. I think the only thing here that might need a bit of calculation, and I don't think we're going to have time for it, is photomultiplier tubes. So I don't think we're going to have much time to go through that. But radioactivity detectors, but it's pretty much, it's just theory, and you guys can just go read through it. Slides and the textbook, please. Like I said, there are some things I haven't included in the slides yet. All right, let's do a quick example on this efficiency calculation, because this also usually have power calculation associated with it as well. So let's quickly do that. Right, so let's quickly go to the textbook. I don't know why I'm sharing the tab. Let me just share my entire screen. Let's see. Okay, so let's quickly check here. So there is an example. I did have it here. I think I scrolled too far. Okay, so there are the different testing methods using X-rays. So if you want to test the material and check it for any flaws or defects, so there's basically you call it. This is the intensification. Justin, I don't even have headings to this. So there's the intensified testing, or so the intensification setup. This is just going to make use of some form of optical or camera transducer thing connected to a monitor. Usually we don't use TV cameras anymore. This is actually still based on old way of doing things. Nowadays it's almost directly stored onto a computer. Then you have your indirect viewing method, where you have X-ray film being developed, and then your direct viewing method, where you as a person actually look at the screen the whole time and at the same time getting lacquer exposed to X-ray radiation. So let's go. Yeah, so there's some other applications here as well, biofuel sorting and grading and industrial process control, aerospace and defense. So quite a few other practical applications. But the example that I want to get to is this here, example 3.3. Right, so I'm not going to go through this example, but this is pretty much a typical question in terms of calculations that you would get with the X-rays. So the textbook, I see the author actually updated the textbook quite nicely, explaining the steps on how to calculate the power. No, the old textbook didn't have this in it, just had the example. But I will demonstrate this by making use of an exercise. So let's quickly do this. Let's take a look at, I believe this is exercise 3.2, yeah, number 6. So let's quickly take a look here. Just make sure I'm still sharing my screen. All right, so, okay, so we're given the following information for an X-ray machine. So we have a high tension supply of 180 kilovolts. We have a target material with an atomic number of 42, and we have a cathode emission. So this is the amount of electrons released by our cathode. You can also read it as the amount of electrons striking our target material, and this is 1 times 10 to the 17 electrons per second. All right, so cathode emission, I'm just going to write as CE in our symbols. There's not really, I don't know exactly what the symbol is there for it, but I'm going to use that. Right, so 6.1, we are tasked to calculate the shortest wavelength of X-ray produced first. So let's quickly do that. So that's going to be lambda is equal to, I'm just going to quickly jump back to the slides here. In fact, let me maybe copy the formula for us, and then it's just going to make life a tad bit easier. Just copy all of the formulas here. So I'm just going to keep this here as a reference. All right, so we want to go calculate the wavelength. So that's going to be Planck's constant multiplied by the speed of light divided by our voltage that we're applying. That's 180 kilovolts. And what do we have here? What's the last thing? The electron charge, which is also a constant. In fact, this electron charge we're going to use again in order to calculate the current needed to do the electron emission. All right, so we have Planck's constant, that's 6.626 multiplied by 10 to the minus 34. And the velocity of light, that is, so yeah, I'm going to cheat a little bit. I'm going to use the 3 times 10 to the 8 just to make things a tad bit easier for us. And then this is then divided by, what is it, 180,000, 180 times 10 to the 3 times the electron charge, which is 1.602 times 10 to the minus 19 coulomb. Right, so that is going to be a somewhat small number if I remember. Well, it's X-ray, so it's going to be a very small number. 6.626. Right, so this is going to give you quite small waveform here, or small wavelength, but that's very high energy. 6.893 times 10 to the minus 12 meters. Or you can write 6.893. Just think, so nano, so minus 6 is micro, nano is minus 9, pico is minus 12. So you can say pico, yeah, 6.893 picometers as well. So either way, the answer is, write it as however you want. Just make sure your units are correct. Okay, so so that is what we have there. Then secondly, we have the X-ray power. So basically the power, so essentially your output power of your machine or your X-ray tube. Now, for this, we are going to require the efficiency of our X-ray tube. So that's then going to be that 1.4 times 10 to the minus 9 multiplied by Z, which is the atomic number, multiplied by the applied voltage, multiplied by 100%. All right, so this is then 1.4 times 10 to the minus 9 times 42 times 180,000. In fact, we can get rid of those 3 zeros. That becomes minus 6. So that is then 1.4 times 42 times 180 divided by a million. Right, so you guys will see the, actually also the 100. Forgot about that one, multiplied by 100. So you guys will see efficiency of X-ray tubes are quite bad. In fact, this one is actually quite good compared to most others. So you're going to get an efficiency here of 1.0. Yeah, let's write it to 2.06%. Right, so there's your efficiency. Now we need to go calculate what the input power is. Then you can calculate your X-ray power using the efficiency and input power. So input power is then going to be the voltage applied to your X-ray tube times the current consumed by your X-ray tube. Now we don't have the current, but we have enough information to go and calculate it. Right, so we know what the charge is, and we know what our electron emission is. Right, so essentially, so if you guys, I don't know how well you guys will remember your physics from high school, but amperes is the same as coulombs per second. Right, so we basically just need to multiply the charge of one electron to our electron emission, and that will then give us our current. All right, so that is going to be our electron emission or cathode emission multiplied by the electron charge. That's going to be 1. Okay, let's just write the electron emission first. 17. I'm sorry, guys. I know I'm going over time here, but I feel that we should go through this. Actually, quite important. This is 1.602 times 10 to the minus 19. Right, so that will then become minus 2. And that is then, that actually really becomes super easy. So that becomes 1.602 times 10 to the minus 2 amps, which we can write as 16.02 times 10 to the minus 3 amps, which you can also write as 16.02 milliamps. All right, cool. Sorry, I squeezed it all in there. All right, so there's our current. I don't know why I picked that as a final answer, because we actually need to go calculate the input power. So let's quickly calculate the input power. Let's do that. So that's now going to be 180,000 volts times 16.02 minus 3. So essentially these two are going to cancel out. So that's 180 times 16.02. And that's going to give you an input power of 2.884 kilowatts. Right, so there's your input power, but we want the X-ray power. Now the X-ray power, let's pick, someone take red there. So your X-ray power, that's going to be your input power multiplied by your X-ray efficiency. That's going to be 2.884 times. Okay, so remember that's a kilowatt value. So maybe let me write it out completely. Times 10 to the 3 times that percentage. So that is 0.0106. Very small number. That is 2.884 times 0.0106 times 1,000. And that's going to give us 30.57 watts of X-ray power. So as you guys can see, you're not going to get all of your input power as an output. Most of your power is actually just going to be wasted as heat. So that's actually the third part that they actually want us to calculate here. They want us to calculate the dissipated power, which is the power lost as heat. So let's do that somewhere in orange because that's a really warm color. And so the power lost as heat, I'm just going to write as P dissipated or P dis. And we can calculate this simply by taking the input power, subtracting the X-ray power from it. So input power, that was 2.884 minus 30.57, and that is 2,853.43 watts. So you can leave it as such, or if you want to write it in kilowatts, that's then 2.853 kilowatts. Right, either answer would be correct there.